So, students, we start with the discussion that we left somewhere. Just a second, please. Yeah. We were talking about an equation. It's a very important equation, that G is equal to G0 plus RT ln A. And we recognize that there is the activity, which essentially is 1 for pure phases. And so for pure phases, this term, ln of 1 is 0, and so this term vanishes. So if the particular phase is pure, then we say activity is equal to 1. If it's impure, then the activity is less than 1, and so the whole term is negative. And if the whole term is negative. But for pure phase, this term being 0, the free energy is equal to G0. That means G0 is the free energy of the pure phase. But if the phase is impure, then the free energy is G, and therefore G is equal to G0, which is the free energy of purity, if you might call it, and this is free energy of impurity, if you call it. Now, yesterday we talked about phase component. We talked about phase components, and another part we talked about, what is about activity, is the active mass of a substance. Active mass of a substance. Now the question is, what does this mean in real terms? What does this mean? Active mass of a substance. Logically, it appears that a part is inactive and a part is active, so it takes in the active part of the component. And I take you back to a definition that I talked to you about the last lecture, was phase component, where I took the example of olivine with Mg, Fe whole twice SiO4, and said that it's composed of two components, Mg2SiO4 and Fe2SiO4. So, if I take say Mg and another term, XMg in olivine. Now, this is a very characteristic way of describing. X subscript Mg, superscript OL. Now, this has a very definitive meaning. Meaning is mole fraction of the magnesium component of olivine, and the magnesium component is defined as this one. So, there you are. XMg olivine, Mg subscript olivine superscript. So this means mole fraction of the magnesium end member phase component to the phase olivine. So if we do this for olivine, then this would be written as, now you see, G olivine is equal to G0 olivine plus RT ln active. That is it. The whole equation transformed to a slightly different situation, where instead now you are talking of the free energy of a particular component in a phase, the active mass of that phase in the equation. So now we have GMG, that means Mg2SiO4, in olivine is equal to XMg0 olivine. That means if activity of Mg in olivine equal to 1, that means this component does not exist. So it's pure Mg2SiO4, then activity will become equal to 1, and this will be the activity of pure and impure. And second is, another point is, all thermodynamic equations are essentially equations of state. So it's path independent. So from a particular state to an initial state to a final state, that's how thermodynamic equations are determined. And so essentially most thermodynamic equations is equal to 0, and it's all path independent. So now, since all thermodynamic equations are essentially equations of state, we need to define the state of the system. And this is done in terms of this formulation. I'm trying to make you understand a little bit about the details of this reaction. So if you do that, then this reaction should be written as olivine pressure temperature is equal to GmG 0 olivine pressure temperature plus RT ln activity of Mg olivine at a particular pressure temperature. That's the final equation. So essentially when you're referring to free energy, and free energy G0 is a function of pressure and temperature, whereas G is a function of pressure, temperature and composition. How does composition come in? Because activity is equal to X into gamma. Or written in the complex way, activity of Mg olivine is equal to Xmg olivine is equal to gamma Mg olivine. So now, this term, G0 is only a function of pressure and temperature. It's not a function of composition because the phase component is pure. But G is a function of pressure, temperature and composition. How does the composition come in? Because activity is equal to mole fraction into what is called the activity coefficient. That is why G is a function of pressure, temperature and composition. So when you talk of this equation, you should know a few things which remain unsaid. That this free energy refers to a particular phase component. I will write it in general terms. I think that will be easy for you to remember. In general terms, it should be written, this is a very simplified way, it's confusing in here. So it should be written Gi phi is equal to Gi 0 Gi phi pressure temperature is equal to Gi 0 phi pressure temperature plus RT ln activity of I in phase change pressure temperature, where I is the phase component, the subscript is the phase component, and phi is the phase. Phi is the phase. I is the one component of that phase. And what is then the definition of G0? What is the definition of Gi phi pt? That means this is the free energy of a phase component at any pressure temperature condition. What is Gi0? Is the free energy of the phase component if it was pure at that pressure temperature condition. That is the important difference. Many students whom I'm not having a class, many students would say this is with respect to standard temperature pressure condition. No, it's not. It's not. It's not. This is something else. You can do it at pressure temperature condition, but written this way, the equation does not mean G0 does not mean that it's STP, standard temperature pressure condition, at 25 degrees centigrade, 1 atmosphere. It's not. Unless you then have to define it that way. Otherwise, thermodynamically, if you write this equation, everyone will take G is pure phase component, is the free energy of the pure phase. in a phase at a particular pressure temperature for the phase to be pure. And this free energy is where the phase is impure. So you don't have to say impure. It's the free energy of a phase component in a phase at an equilibrium pressure temperature. Pure or impure, it doesn't matter. If activity is 1, this will be equal to this. Having said this, we could have switched over to something that I would like to say, but I think I will talk to you a little bit about, very little bit, about what essentially is a solid solution. Now, before we go into that, we will do a few things. Okay. Okay, let's start. Now, you must understand again before we go in, G0 is a function of pressure and temperature, not composition. G is a function of pressure, temperature, and composition. We will go a little bit into activity before we switch over to ideal mixing, etc. As we know, A is equal to X into gamma. Remember, I, phi. The subscript is the phase component, superscript is the phase. Now, this is a diagram where I plot activity versus composition. Many of you know it, but I think it's good to recap once in a while. And I draw this line here. You can understand it's a 45-degree line. Along this line, activity is equal to X. Now, you see, I am dropping I phi because it makes us a little easier. We have a small board, and so it's a little easier. A is equal to X along this line. Now this is where gamma should be equal to 1, because if A is equal to X, gamma should be equal to 1, very simple. Now these type of solutions, these type of behaviors are called ideal solutions. These are called ideal solutions. I will come to solutions in mechanical mixture in a while. Say, for example, we take the matter of olivine. It has Mg2SiO4, Fe2SiO4, which is not a mechanical mixture. It's not salt and sugar, but it's a solid solution between the two phase compounds. So along this line, A is equal to X. But there could be a possibility where A is not equal to X. And therefore, it's important, gamma is not equal to 1, and these are called non-ideal solutions. How will they look like? They can look very differently, but a very simple way is like something like that, or it could be something like that. In this case here, A is greater than X, that means gamma is greater than 1, and here A is less than X, and therefore gamma is less than 1. That's what it is. Both are non-ideal solutions because gamma is not equal to 1. The important thing that you should remember here is, if you take a slope of this line, slope at any composition. You see, this is the composition line. If you take the slope of that line, say for example, I draw a slope tangent like this, and this is my tan theta angle, then this slope is equal to A divided by X is equal to gamma. Have you understood? A divided by X is equal to gamma. Now you see, in an ideal solution, A by X is equal to 1. Have you understood? Because gamma is equal to 1. A is equal to X, gamma equal to 1. So gamma is independent of composition. Gamma, the activity coefficient, is independent of composition. But if you are on these curves, here you can see this is what is A by X, this is the slope of A by X, this is the slope of A by X. So the A by X slopes essentially change, and change as a function of composition. As a function of composition, it changes. So one of the characteristics of non-ideal solutions is that the activity coefficient is a function of composition. Activity coefficient is a function of composition. Now you can see, if I take this term, for an ideal solution, A is equal to X, gamma equal to 1. For a non-ideal solution, A is not equal to X and gamma is not equal to 1. So this you should remember very, very carefully, that in an ideal solution, A by X is equal to 1. That means the activity coefficient is independent of composition. Whereas in a non-ideal solution, the slope of the line changes, which is A by X. And this is a function of the composition. And that is why in non-ideal solutions, gamma is not equal to 1 and activity becomes completely a function of composition. Have you understood? So if we now go back, okay, just one thing before we go back to the equation. You look at this part, this is an interesting part. This is where X is tending to 0. X is tending to 0. You see what is happening here? The non-ideal solution curves are becoming parallel to A is equal to X curve or ideal solution. That means for at very low values of X, and this there is a term for it, it's called infinite dilution. So if there is a component which is tending to 0, limited to 0, that means it's being it's at infinite dilution. Then non-ideal solutions and ideal solutions lose their identity. So you have, at this point, non-ideal solutions can be approximated by ideal solutions at infinite dilution. This has many advantages, but we will not talk about it since it's not within this thing. But this is very important to understand, that at infinite dilution of X, you can ask, why not this part? Here I have I, but if I took the other component J, this would be when I tends to 1, the other component J tends to 0. Have you understood? That's important. When I tends to 1, the other phase component that make up the composition of the phase tends to 0. So when you say 1, it also means Xi tends to 1 means Xj tends to 0. That means J is going into infinite dilution. Right? So this is looking at it in the reverse way. That's all the differences. So it's very important that when mole fraction becomes very small, very, very small, then activity coefficient, all solutions tend to become ideal solutions. It's easy. Why? Because the mole fraction is independent of activity coefficient is independent of composition. But at non-infinite dilution portion, in a non-ideal solution, activity is a complex function of the composition. Right. Now there becomes an interesting point here. Before we go into that, before we go into further studies, I will emphasize this. G0 is a function of pressure and temperature. It does not depend on the composition. But activity itself is a function of composition. In ideal solution, the function is not independent of composition, but if it's a non-ideal solution, it's a function of x. But here, G is therefore a function of pressure, temperature, and composition. So this pressure and temperature, this builds in the changes in G because of the change in the pure phase. And this adds to the compositional value. Or in another way, G minus G0 is equal to RT ln activity. G is equal to G0 plus RT ln. So you see, whichever way you write it, manipulate it, this difference is a function of the composition. So, just before we conclude on this part, it's important for me to tell you that we can write this as G is equal to G0 plus RT ln xi phi, gi phi, gi phi. This only means we are considering ideal solution. Now, I think before we go into more details, I think I should tell you a little bit about mechanical mixture and solid solution. We'll do it. I think it's important to understand. Because those who are in geology, they will always have this at the background, playing at the background. Those who are working with mineralogy, petrology, geochemistry, it's always playing on the background. So you should be very, very conversant as to what is being played behind the mind. The teacher may not be saying it, but it's played in the background. It's always there. Now let's say, I told you, G0 is a function of pressure and temperature. So, at dP is equal to dt is equal to 0. That means at a particular pressure temperature. How G0 is expressed, we will go a little bit into that. There is no space, this is not a thermodynamics class, so I cannot do that. But for the moment, at dP is equal to dt is equal to 0, that means at a constant pressure temperature, G0 is a numerical value. So now, let's draw a diagram. This is mole fraction. And let's say we take this as G0. We take this as G0, and I have to now write A. That means, what is it? You have to understand. This means that at a particular pressure temperature condition, at this point, that means XA is equal to 1.0. Remember, activity will be equal to 1, therefore the term vanishes. So this will be G0A. And let there be another term, another component, B. the other component that make up the phase. You can write here A comma B, alpha is the phase. Or like for example, we wrote Mg2SiO4, Fe2SiO4, and then we wrote Mg comma Fe whole twice SiO4, something like that. So this is our A and this is our B, let's say. And let's say the phase is alpha. Now you see, this also then should be GB0. Now, if I mechanically mix A and B, the free energy of the mixture should lie on a straight line joining G0A and G0. If A is a pure component and B is a pure component and they are mixed mechanically at a particular pressure temperature, then the free energy of the mechanical mixture should lie on a straight line. So we can have a situation where we can talk of G mechanical mixture of, say, alpha. Remember, alpha is the phase. Okay? Or G. We know this. G mechanical mixture. Now, if you have to say mechanical mixture, then you have to define a composition. So let's say I take a composition here. So if I take a composition here, this is the amount of XA and this is the amount of XB. This is XB because this is 0. So XA would be from B is equal to 0 and B would be from XB is equal to 0. So this is XB into XA. This point could be anything. But G mechanical mixing would then be written as XA GA0 plus XB GB0. Tell me, have you understood it? XA GA0, that means the mole fraction of A into the free energy of the A, which is pure, and XB, which is the mole fraction of B in the phase, and multiplied into the free energy of B. So you have this equation, G mechanical mixture is equal to XAGA0 plus XBG0. This is the line on which the mechanical mixture would lie, and this would be the free energy. If you shift this point here, then you will see XA will become 1. If you slide this point from here to here, XA will be 1 and XB will be 0. So it will be G0, of course. And if you slide this point to this place, then it will be XB 1.0 and XA will be 0. That means G mechanical mixture will be GB0. But what will happen if they are not mechanically mixed, but A and B form a solid solution? Form a solid solution. Remember now, for a solid solution, activity, if you don't like it, then we can think of the term mole fraction. So what will happen? The G will be lower than G0 for a solid solution, obviously. So the free energy of the solid solution should lie at this is G, at a free energy lower than this line. It has to lie lower than that line. So what will happen is, this is what will happen. The solid solution line will lie lower than the mechanical mixture, but at the end members they have to be pivoted. Have you understood? They have to be pivoted at the two extremes. But overall the line should lie lower than the mechanical mixing line here. This is the mechanical mixing line, and this is the solid solution. So the solid solution line should lie lower than the mechanical mixing curve. Why? Because in a solid solution, you have the activity term or the mole fraction term, whichever you want, and this will be negative for an impure phase. And for a pure phase, it will be the same. So now, say for example, let's say this length here. I am drawing this in bold and giving it a name called G mix. G mix. So, for the G solid solution, I can write G mechanical mixing plus G mix. Now, this addition is algebraic in nature. Algebraic in nature. So, essentially, G mechanical mixing is here, and you add algebraically, add G mix term to this, so you should get back into the G solid solution line at the same composition. Once again, this is the equation of mechanical mixing, and this is the solid solution. From the mechanical mixing, if you algebraically add G mix, then you come back to this point. So, essentially, G solid solution should look as XA GA0 plus XB GB0 plus G mix. That is how it should look like. G mix should be negative. I'll give you a little time to think about it. Right? So, from mechanical mixing, you're here at this composition, you're here, and you add G mix, which is negative. You can say, I could have subtracted, it doesn't mean anything. It means plus minus G mix or minus plus G mix. G mix, it does not get. So what you do is, you add G mix. But there is another way to do it. I take this point. On the G, on the solid solution, and draw a tangent to that point. So what will happen? This is the tangent to this point. And this tangent intersects A and B at this point and this point. Have you understood? Now what is this point? This point is GA. And this point is G. So this point is GA0. This point is GA. So G solid solution can also be written as XAGA plus XBG. XAGA plus XBGB. Now let's look a little bit inside. What is GA? The free energy of the impure solid. GB is the amount of B impurity in the mechanical mixture. So it is a mechanical mixture of the GA and GB. This is a mechanical mixture of GA0 and GA0. But this line is not that of a mechanical mixture. It is of a solid solution. So we come to this very important relationship. And now we can write if we make this as equal, then we can write G mix is equal to XA GA minus GA0 plus XB into GB minus GB0. Do you understand this? G mix, therefore, if we equate these two equations, G mix will be XA GA minus GA0 plus XB GB minus GB0. If we do this, then we come to this relationship now. What is G mix? If I write this is what it is, because GA minus G0 is RT-LN activity and GB minus GB0 is LN RT-LN activity. So essentially G mix is XA XA activity A, XB LN activity B. If we translate this to an ideal solution, we won't go into more details because I think we have to stop somewhere. So G mix will be equal to RT XA ln XA plus XB ln XB for ideal solution, if you ignore the gamma terms in the activity relationships. Tell me, have you understood this? Now it is important to realize, if we slide this point to here, you see this G mix does not have the same energy difference. It tapers off towards A and this tapers off towards B. It becomes 0. So if you take this point and slide it to where XA is equal to 1.0, then you can see XA is equal to 1.0, so this is 1, and this one, ln of 1 is 0, XB is already 0, so the whole term is 0, so G mix is 0 when XA equal to 1.0. Look at this, if you slide this point here, XA will be equal to 1, ln XA will be equal to 0, so this term will be 0, and at this point, XB is equal to already 0. So this term will be 0. So G mix will be 0. The same thing will happen if you slide this point to B. G mix will be equal to 0. There will be no energy of mixing. What is G mix? G mix is essentially this gap. At any composition, this gap. The difference between mechanical mixing of the pure components and you can say mechanical mixing of the impure components. But when you say impure component, it means already a solid solution. It already means a solid solution. So, G mix is essentially the difference between mechanical mixing and solid solution. And then, of course, G mix then is a function of composition, as you can see, either here or here. G mix is a function of composition at constant pressure temperature condition. It's still a function of composition. But at the two ends, both G mix at XA is equal to 1 and at XB is equal to 1, it's 0. Because there is no solid solution. There can be no solid solution for a pure phase. Now I think the difference between these two comes clear to your mind. In the figure, this, can you see this? This term is RT-ln activity here. This term, GA0 and GA. The difference between that is RT-ln activity A. So this essentially is RT-ln activity A. And you can see, if you slide this point along the solid solution line, you will see the line will move like that. The line will move like that. So these are not constant values. These are very different values. They can change from 0 to a very large value. 0 it will be where A is a pure phase and B is a pure phase. It's like driving a car. So it's pivoted at this point and the line simply moves. So this point here is GA0, GA minus GA0, and that is RT-ln activity A. And here, GB minus GB0 is essentially RT-ln activity B. So this is what is important for you to realize here at this point of time. The importance of the equation. So I will erase it. I'm going no further. A lot of things can be done from here on, but it's not necessary at this moment. So here then we have G is equal to G0 plus RT-ln activity. I, phi, and obviously pressure temperature because it's an equation of state. This is the meaning of this fundamental equation that controls chemical thermodynamics, not only in geologic systems, but all systems. That's the fundamental equation which deals with chemical thermodynamics. Right? So, this is what I wanted to emphasize. Now, okay, I think I will stop here. Next class I will talk to you about other things about binary phase diagrams. Thank you. So we come to the conclusion of the 12th lecture in 3 weeks. And if you have any questions, please feel free to write me a mail. I can post it without your name on the Google Classroom post. But I think it's important that if you don't understand something, it's important to come out and say. So when I put the post, I don't put your name, so that it's just a question from one of you. So you don't have to feel shy that, okay, I don't know, somebody else knows. You don't have to go into complication. You just write a personal mail, the mail that is there already, and I will give you the answer as quickly as possible, same day always, maximum next day if I'm not indisposed. Okay? Thank you very much. And another small thing that I would like to say is that I have to take 4 exams. This I told you in the very first slide. We are coming to the point where we have to conduct the exams at the end of this month. So how to conduct, when to conduct, I will let you know. But I think you should gather up, buckle your belts and start reading, because it's very important. The classes, the test will be held on the first 8 lectures. On the first 8 lectures that I sent you, lecture 1 to lecture 8. Or maybe I could do one thing. I could take a test from lecture 1 to lecture 4 if you're interested. I think I will take a test on lecture 1 to 4, and then we can extend this lecture to other classes. I will tell you when I will take the exam, but it should be at the end of this month, near the end of this month, and make sure that you have studied well. If you have not studied and you get, all 25 marks, and if you don't get a good mark in your first exam, you are almost losing a very high percentage of marks. So I will tell you there is still time. Those of you who have not yet got into the groove, please get into the groove. Please get yourself educated. We will have the first 4 slides of my lectures. We will have an exam on the end of this month. I will let you know the time and the date soon enough. Right? Thank you.